Hello everybody, this is the Primal Earth, and today we will be talking about gigantic stars. And when I say gigantic, I mean gigantic. This is the sun. You want to know how big the sun is? Take every single atom of everything in the solar system except for the sun. That includes everything from Jupiter, from the largest gas giant, Jupiter, to the smallest speck of dust. Now the sun, all that is a ton of stuff. It only takes up 0.02% of the solar system. The sun takes up 99.98% of everything else in the solar system. 99.98% of the matter in the solar system is inside of the sun right now. That is how big the sun is. Many people think the sun is a huge star. Let me tell you something. The sun is tiny. This is a red supergiant. The red supergiant is gigantic compared to the sun. It's just huge. You cannot get a bigger. It is one of the biggest stars in the universe. When this thing dies, it produces an explosion so large that it puts out more energy in 1 second than the sun will ever put out in its entire lifespan. Almost said lifestyle. That's how big an explosion a supernova is. But what if I told you that a supernova wasn't the biggest explosion? Well, you'd say, of course, there's the Big Bang. Well, the Big Bang was actually an inflation. Ever heard of inflation theory? We'll probably do some of that sometime soon. But not even Betelgeuse, a red supergiant. Nothing can contend to VY Canis Majoris. Actually, well, this is the biggest star I could get. See that tiny, 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 tiny dot? Let's go up to the sun. Let's put its distance out a little bit. Okay. So. See that tiny dot? Right where the mouse is. That is our sun. That is a supergiant. This is a hypergiant. See, look. These stars up here are bigger than our sun. And our sun looks like a tiny little dot. But this is the largest star that will ever exist. It is such a massive star. Actually, no. I think it's VY Canis Majoris, but I'll put an annotation up or something. Actually, no, because annotations can't view it. I'll put the name of the actual largest star up here, because I think VY Canis Majoris is no longer the largest. But we're just going to pretend this is VY Canis Majoris, because it is the largest star that I like to talk about. It was a hypergiant. In fact, it probably still is a hypergiant. Hypergiants are so large. Okay, so when you blow up a supernova, you'll create one of three things. You'll create a neutron star, a pulsar, or a magnetar. Now, let me tell you what a pulsar is. A pulsar is a star that spins so rapidly it shoots out two beams of supercharged matter and light particles. We'll do a separate episode about the beam because there's a huge common misconception about that beam. It shoots out two huge beams of radiation from the North and South Pole as it spins rapidly like a spinning top. The magnetar is so magnetic. It is the biggest magnet in the entire known universe. if you come within 10 light years of it, well, no, come within a light year of it, no, because that wouldn't work. I can't remember. No, okay, I remember. If you come within 10 million miles of a magnetar. Now, a magnetar, let me tell you something. It's only 6 miles across. A white dwarf that forms when the sun dies is the size of the Earth. Now, you're taking something that's 6 miles. That's the size of the asteroid that wiped out the dinosaurs. Now, that asteroid killed off only 75% of life on Earth. A 6-mile magnetar at 10 million miles away will wipe every debit card and credit card and any card that uses magnetics or stuff like that. It will wipe them clean. So, if one day you wake up and your credit card is wiped clean, and someone else's is also wiped clean, and everyone in your neighborhood has also been wiped clean, and everyone on your that you call is wiped clean, you're gonna know there's a magnetar at least 10 million miles away. But then, at that point, it'd already be too late, because magnetars are also extremely gravitational, and they will sling objects at you. So, by the time you realize there's a magnetar, you're probably already going to be dead. A neutron star is just a pulsar. Well, it doesn't shoot beams, and it's not as magnetic, but it is very dangerous. Very dangerous. Those are 3 things that can be produced by a supergiant. What can be produced by a hypergiant when it explodes? Only one thing. But that one thing happens to be the worst nightmare of anyone who ever existed. Imagine. There's a hole that appears. It starts to suck things into it, and then the atoms in your hand start to rip apart. Your hand gets stretched out as the flesh rips and tears off you. The bones start to stretch and crack. Your fingers become strands of spaghetti as all this stuff is being drawn toward this hole. This is a black hole. The most terrifying object in the universe. The only thing that can challenge it for ferocity is the explosion that creates it. As you could probably tell by the title of this video, we're not talking about black holes or magnetars, pulsars, or neutron stars. We're talking about the biggest bomb in the universe, a hypergiant. Let's start. Okay, so take a star bigger than the sun that would stretch out to approximately half a light year. A star, well, actually, Betelgeuse would stretch out all the way to Jupiter. This guy, it would stretch out to Neptune. That's how far this VY Canis Majoris would stretch out. A star so large that the sun could orbit it like a planet. That's how small the sun is. This little thing right there could orbit that star. This is a star so big that when it explodes, the brightness of the entire galaxy would be less than the explosion this thing creates. Supernovas can do that too, you may say. And yes, supernovas can do that. But you know what supernovas can't? Well, I'm not sure that they can't, but I'm pretty sure they can't. They can't create a gamma ray burst. A burster of gamma rays shot out from the poles of the star. A beam of gamma rays that goes like a blowtorch, blowtorching the entire galaxy. This is a gamma ray burster, and it comes after the black hole is formed in the inside and ejects millions of tons of debris out at the speed of light. If you get caught in that beam, your planet is toast. Quite literally. Everything will be scorched. The atmosphere, gone. And that magnetic field ain't gonna protect you this time. Nothing can protect you from a gamma ray burst. Unless you have maybe a planet that's like 10 times your size. Like directly in front of you. And maybe. But, you're probably gonna die. A monster of a star. So gigantic that it wouldn't explode. So, let me give you a little fact here. You probably didn't know. There was almost a World War III. Okay, you probably knew there was almost World War III. It probably happened a lot. But there was one time. So let me tell you, let's go all the way back to after the Cold War was over. Now, we had all signed a treaty or something that said we would ban the testing of nuclear weapons. Okay, so that. Now, to make sure that the Russians weren't testing nuclear bombs, we sent satellites out into space. You know what they detected? They detected shock waves and radiation similar to that of a nuclear bomb. It was the Russians. The Russians were testing nuclear bombs. Not on Earth. No. Tsar Bomba created an explosion so big it was taller than Mount Everest. Many, many times taller than Everest, the mushroom cloud. And it shattered windows thousands of miles away that weren't even near the testing site. So, you would know if you were testing a nuclear bomb. So, the Americans thought, what an ingenious idea. The Russians were testing nuclear bombs in outer space. But then, we checked. Just to make sure. Before we fired nuclear bombs at them. Those nuclear bombs weren't even in the Earth-Moon system. We looked farther. They weren't even in the solar system. Okay, now we're starting to think. Not even a single spacecraft. Voyager, hasn't even passed the heliopause. Or I'm drawing a blank. I think it's heliopause. Or it hasn't even got past our solar system yet, Voyager. It's still in our solar system right now. It's at the edge, but it's not at the it's not into stellar space. So the Russians had figured out a way to send nuclear bombs out of the solar system. But then we checked again. They weren't even in our own galaxy. Surely the Russians could not fire a nuclear bomb outside of our own galaxy. So then we checked again. And guess what we found? These nuclear blasts were coming from the entire opposite side of the universe, near the cosmic microwave background. 13 billion light years away was where these explosions were coming from. Now, there's no way the Russians could fire a nuclear bomb to the entire opposite side of the observable universe. But you know what was even more shocking than that? Okay, so if you take a gamma ray beam of light and you fire it, eventually, what was that? I would put something of it so you cannot see what it said. Okay, so back to the regularly scheduled program. So, if you take a nuclear bomb, why was I saying? So if you take a light beam, a gamma ray photon, fire across the galaxy, eventually, say maybe a light year, it would turn into just a radio photon, or something like that. Something that wouldn't kill you if it struck you. It wouldn't be effective. So, over a light year, gamma ray loses energy and becomes harmless. Now, for there to be a gamma ray beam that goes from the edge of the universe, 13 billion light years away, to us and is still a gamma ray beam, it's got to be something pretty intense. Now, when you take the fact that there is a... Now, this isn't just a gamma ray beam. This was an entire explosion big enough to trick us into thinking that Russians were testing nuclear bombs right near our planet. Right near our planet. And there was gamma ray beams that strong. That should tell you something. There was a pretty big bomb exploding on the opposite side of the universe 13.8 billion years ago. For that intense beam to fire across the universe and end up at Earth and trick us into thinking someone was testing a nuclear bomb a few miles away. That should tell you something. That is how big that a gamma ray burst can be. And the explosion, it's enough not only to be brighter than an entire galaxy, but to outshine the entire galaxy. That is how much energy is put out when a massive hypergiant star explodes. Pretty deadly. Nothing could compare to the gigantic hypergiant star. Nothing can compare. It is the largest bomb to ever explode. Tsar Bomba, the biggest bomb that we ever created, was 50 megatons. The asteroid that killed the dinosaurs was 1 million times that of the Hiroshima bomb. There is just no way to describe how big an explosion would be from a hypergiant star. An explosion from Tsar Bomba, the original one, because there were actually 2 Tsar Bombas, One of them was the 50 megaton that was exploded on this Earth. The other one was designed, and it could have worked, but they just didn't build it because of how powerful it was, and they could not predict what would happen after they exploded it. So they cut it down to 50. It was 100 megatons. That 100 megaton nuclear bomb would just be like a little breeze. A little tiny breeze. Compared. Not even a breeze. It'd just be like an atom pushing against another atom. Compared to a hypergiant explosion that is the hypernova. You've all heard of supernovas. If you haven't, what are you doing with your life other than not watching how universe works or stuff like that? You're probably off doing something cooler than that, but it's okay. You're here at this channel, so you probably like this. But anyway, think about that. There was an explosion so big, they had to rename it. There's type 1A supernova, and then there's the regular supernova. Type 1A is the white dwarf and the giant star. Giant star sends gas to the white dwarf, then the white dwarf explodes. That's, I think, type 1A. I'm not sure. It might be something else. But they already had something that it was called. It was called a supernova. But then they figured out that there was something millions of times bigger. They didn't keep supernova. They changed it to hypernova. They created an entirely new name for this explosion. That's how big it was. They changed the name. Now think about it. It has to be pretty significant for you to change something's name. I'll talk about Manospondylus gigas on a future episode. Because, they did change the name. And that was pretty significant. I'll talk about Manospondylus gigas in a future episode. But right now we're talking about the star. So, you'd have to have a pretty big explosion. It has to be, that is very significant. For us to already have a unit that's okay for the name, but for it just to be such a big explosion that we'd have to rename it, that is one gigantic explosion. There is no way that you can comprehend such an explosion. There's no way. But you know what's even scarier about that? Even if you weren't in the immediate gamma ray beam, if you were 10 light years, now think about it. Think about how far that is. 10 light years. The closest star is closer than 10 light years. Twice as close as 10 light years. If you were 10 light years away, even nowhere near the gamma ray beam, you would die from the explosion. That is how far away you can be and still die from the explosion of a hypernova. That's pretty immense. You cannot comprehend 10 light years. There's no way. Because the solar system isn't even a light year wide. At most, from one end to the other, it would be 1.5, maybe 2 light years at its most across. You cannot comprehend the size of a hypernova. It is the biggest bomb in the entire universe. The only other explosion comparable to a hypernova, well, actually, it'd be the other way around. The only explosion that you can compare a hypernova to is the Big Bang. Unless you believe in inflation theory, of course. Then hypernovas are the biggest explosion that the universe has ever seen. But, you know what's even worse? WR-104 stands for Wolf Riot. Now, for those of you who know what WR-104 is, you'll know what I'm talking about. WR-104 is a hypergiant star. It's not big. It's bigger than that. It's not as big as supergiant, but it's pretty big. It's a hypergiant star, about 100 light years away. So we'd be safe from the explosion. We're way far away for that. But our solar system is staring down the gun barrel of a gamma ray burst. When WR-104 dies, it's going to eject a gamma ray burst. And our solar system is directly in line for the shot. Now, in the previous episode of The Science of Space, I talked about how the Earth, well, actually I didn't state this in the actual video, but I'll state it now. Most people think the Earth has 4.5 billion years left until the sun dies. Well, sorry, tough luck. It only has 1 billion years before bad things start to happen. Well, if the WR-104 does blow up, and we are in the sights of the gun barrel, we're only going to have 100 years left. Now, that is very unlikely that it's going to actually hit the Earth, because the Earth is such a small target. This is the sun. Wait, where'd the sun go? Let's see if we can get the sun back. Wait, we're gonna play a game. It's called Find the Sun. So we can make the sun really big. That's not the right one. This is the right one. Okay, so oh, there it is. Right there. That's the sun. The Earth is 1,000,000 times smaller than that. So we shouldn't really be worrying that much from the gamma ray burst of WR-104. But we should still worry a bit. Because there's always the chance that we could be staring down the gun barrel. Because we are in a shooting gallery. And the Earth is a very small, but very big at the same time target. Because for all of the shots fired that misses, there's for every 10 shots that miss, I think the odds are that there is one shot that will hit. So, the Earth is not safe. We do not live on a happy planet. Everything in the universe is against life. Life is a cosmic fluke in the universe. It happens just by chance. If the right ingredients are put together, you will get life. The universe was not built to hold life. But you know what was built to contain life? Planets. But you know, planets were not meant for this universe. The universe had stars. And that was all they needed. They only needed stars. The universe was built for stars. Nothing more and nothing less. But then, when stars don't grow big enough to take up all the material they were built from, planets form. The universe was not made to have planets, but planets formed anyway. But then, on those planets, life formed. And every single thing. Planets can take a beating, alright. And the Earth is pure proof of that. Something the size of Mars crashed into Earth, spilling out the guts of the Earth. But you know what? You know how I know the Earth survived? Because I'm sitting here talking to you right now. Planets can take a beating, but life, it can take one rock to take out life. One rock, 6 miles wide, wiped out 75% of everything that ever lived on the planet, at the time. And if the Permian asteroid theory is correct, a rock 7 miles wide took out 95% of all life on Earth. Rocks, just 7 miles wide, can take out every life form on Earth. The universe was not built for life, but life is one of the most resilient creations the universe has created. So, that is the episode about hypernovas and giant stars. So anyway, thank you for watching. Make sure to leave a like, forget to leave a dislike, and have a fan-flip-tastic day and a Merry Christmas or Happy Hanukkah. So this has been the Primal Earth, signing out once more. Thanks for watching. And we are out.